Okay, so today I want to give you the third example from my slides on how to optimize with a constraint that's written in the form of an equation. Um, Later on, we'll talk about what happens when it's an inequality as opposed to an equation. But for right now, there's one more example. I called it example 3 in my slides. And it has to do with a different sort of budget constraint. It's the type of budget constraint that is intertemporal. Intertemporal is the fancy word for meaning across time, not just right now, but also you're thinking about the future. That's an intertemporal problem. And in this problem, there is an interest rate, which is fixed, constant interest rate. And that means you can either borrow money now and pay it back later with interest, or you can save money now and generate interest. And I decided, as is often in these problems, just to make the interest rate the same. When in reality, if you wanted to borrow money, you'd have to pay an interest rate, and that rate would be higher than the interest rate you would get if you were saving money. That's how banks make money. They charge you a different rate than they can get. Okay. So in this problem, you're a consumer and you want to consume goods and services now, but you also want to consume goods and services later. And there's a trade-off between consuming anything now and waiting to consume it later. And the trade-off is exactly determined. The rate at which you can trade this consumption now versus consumption later is determined by the interest rate, R. In fact, it's going to have a slope of 1 plus R. But let's look at the exact problem. I'll share it with you. Should be here. Gonna have to wait for the thing to pop away. Okay, this is an example 3, which is about optimal saving or borrowing. And by that, I mean, you have the choice. You can either save or borrow. You can't really do both. It wouldn't make sense to do both because you'll either have a net saving or a net borrowing. That's what we're talking about here. But let's talk about a consumer whose income is fixed. It's exogenous. It's M1 in period 1. That's how much income you receive in period 1. And you're going to receive income M2 in period 2. And you know these ahead of time. You know exactly what your M1 and your M2 are going to be. Now the consumer will choose to consume. This is the choice variable, C1, in the first period. You can choose how much to consume in the first period. If you consume less than your period 1 income, you save the rest. And what you save will earn interest at a rate of R. In other words, it'll grow by a factor of 1 plus R. If you save $1 in the next period, it will grow to 1 plus R dollars. If you save $100, it'll become 100 plus 100R, or 100 times the quantity 1 plus R in period M2, or period 2. And whatever you save, that will be added to your second period income. So you get M2 plus what you saved. And then that amount, which we'll call C2, that's what you consume in the second period, it will be totally consumed in the second period. There's no more savings until a third period or a fourth period. We're just looking at a guy who has 2 periods, now and later. That's it. And so you can save money if you consume less than your income. However, you can also consume more than your income. This is what I think a lot of you youngsters do with credit cards. You're allowed to actually buy more stuff than you have money if you borrow money. Of course, you can do that, but you have to pay it back with interest later at a rate of 1 plus R. Okay, so this is an intertemporal or consumption problem. What choices of C1, that's your first period consumption, and C2, your second period consumption, will maximize the utility? Here's what, here's what the functional form of the utility function will be. The natural log of C1 plus the natural log of C2. It turns out natural log is actually a pretty good approximation of people's utility. In the sense where if you think of consuming 0, If your consumption was zero, that would be really, really bad, right? You'd have to live your life spending nothing on anything. You have to, you'd be eating garbage or whatever people give to you for free. You'd be sleeping, you'd be homeless. You wouldn't be able to afford a rent, or you'd have to stay with somebody who's letting you stay with them for free. But the idea of your consumption going all the way down to zero, the amount of money you spend on buying things goes all the way down to zero. That's really bad. Well, natural log has this property that if the C goes to zero, natural log goes to negative infinity, right? That's like, and in terms of utility, that's the worst possible utility, is if you let C go to zero. And then once consumption grows, it sort of flattens off, where it's always more is better, but the rate at which your margin utility gets less and less as you grow. I think I'm just saying natural log is a common choice for a utility function when you sort of bundled it all together to say, this one number is your total consumption. It's called C1. How much utility do you get from C1? Log utility is often used. Okay, what's the budget constraint for this problem? Does anybody want to try to answer this? This is tough. It's not easy. I'm asking you, what is the equation which describes how much C1 and C2 I can choose? It's going to involve M1, it's going to involve M2, and it's going to involve R in C1 and C2. The question is how? How do these five terms work together? Anybody have any ideas for this? Who can see what you share here? Recording on. Okay, that seems like that's new. I don't need this, right? Or do I? Does anybody have any thoughts on just how would we write the budget constraint for this problem? You have to think about the fact that I might be saving money or I might be borrowing money. You might think that you need two different equations. One equation if you're borrowing, one equation if you're saving. It turns out you don't. You can simply talk about however much more you're consuming or less than you're consuming, and leave that as a number that could be positive or negative. In which case you don't need two different equations. One equation will work here. And it might help to see a graph. I'll show you the graph. That might help. This is the intertemporal budget constraint, where on this axis is your consumption in period 1. This axis is your consumption in period 2. This point here is kind of special because it's if this is where you would consume if you didn't borrow and you didn't save, you just consumed M1 in period 1 and M2 in period 2, you would be right here at this point. Now you see this red line it's a way for you to increase your options. You actually don't have to consume at this black point here. If you want to borrow money, you can go down and to the right, and this would be equivalent to borrowing some money to consume more in period 1 but less in period 2. Or you could go up and to the left. This would be equivalent to saving some of your period 1 money, generating some interest on it, and consuming more in period 2. But remember, your utility is log, and therefore you would never want to get even close to these edges here, C1 or C2. That's the disaster one, where you're homeless and you're eating out of garbage cans. So it's a real problem here. This is a real optimization problem. It's non-trivial. And the first step, I think, is to write the budget constraint. And even that is not easy. Does anybody have any guesses or just any ideas what to do? How about, well, do you want to use this, the slope of this line? You want to just describe the slope of this line if you can. Let's do this. I have two ways to think about it. I'll give you one way, and then the other way will be one on the slides. So right now, I'll talk about the way that is not the one that's on the slides. And that is slope intercept. to describe this line using the slope of the line and the intercept of the line. Let's do that. Okay, so the y-axis is C2, so we'll call that C2 equals. What does C2 equal? The slope of this line times the x value. What's the slope of the line? Well, I've written it right here. I guess that's cheating, but maybe it's worth saying, why is the slope of this line -1 plus r? It's because if you save $1, you get to consume 1 plus r more dollars. So imagine a little triangle here. It was like $1 of saving corresponds to 1 plus r dollars of extra consumption. What's the slope of this line? Well, it's negative, you can tell, because it's going down, and it's rise over run, 1 plus r over 1, it's 1 plus r. That's where this comes from. Get that? This is like algebra now. We're talking about high school algebra. Hopefully you remember your high school algebra. Okay, so the slope of this line is -1 plus r. The formula for slope intercept is that it's the slope times the x variable. So I'm gonna put -1 plus r C2. And now we're still not done. We have maybe a difficult problem here, which is to calculate the intercept, which is not easy, which is why actually I don't use this formula. Erase this. So how do I figure out this intercept here? Well, I can use the fact that this point here is m1, and this distance here is m1. So this distance here will be 1 plus r times m1. All right, and by the way, right now I'm just talking about this distance. But if I want to know the value of this slope, I have to add that to m2, because I want this whole distance here will be this plus m2. So the intercept is actually 1 plus r m1. Okay, all of this to say this is a budget constraint plus m2. If I did it right, I think this is right. Is this distance here is m2. So I add this distance plus this distance. That's the intercept, which I've written here, and this is the slope. So this is like the normal slope intercept form for it. Oh wait, where's C1? Ah, you guys were supposed to correct me here. This should have been C1, not C2. Better not use that for my thumbnail for the YouTube video because it's wrong. Here, C1. That looks right, doesn't it? So, okay, you could use this. Also, remember when we write, we're going to end up using the method of Lagrange multipliers. When we do that, we want our, we usually write things as something equals 0. So what if I just, in the interest of, I kind of would like to do is make the C1s positive. Actually, no, being negative is fine. Being negative is fine. Negative C1 minus -1 plus r C1 plus 1 plus r M1 plus 1 equals 0. I think that is going to be a fine budget constraint, unless I made a mistake. Do you guys see anything wrong with what I did? I think it's right. It's a way to define basically all the points on this red line, which is, that's what a budget constraint is. That's what a constraint is. It's saying you can't just pick any value of C1 and C2 that you want. You have to pick some value of C1 and C2 that's on this line. And the method of Lagrange multipliers, it says, okay, we'll take that constraint, we'll form one equation out of it, and we'll multiply a variable to it called the Lagrange multiplier, which we usually call lambda. And then we'll include that as part of add that to the objective function, it becomes the Lagrangian function. And then if we take the first order conditions of that and solve those simultaneously, we'll get the answer to the constrained optimization problem. That's the method. So if we do that here, I can write the Lagrangian, I think. It's L should be equal to the natural log of C1 plus the natural log of C2, and then plus lambda times this whole thing, negative C2 minus 1 plus R C1. These constants don't matter. Should I put them in? I'll put them in, but they don't matter. They're not gonna. Oh, of course they will matter for the constraint. That third. Oops, this isn't my way now. Gotta move this. M2, something like that. Right? I think this is a good formula for L, the Lagrangian function, because we have our objective function right here, our multiplier, and our constraint. Do you guys see how I got this far in this problem? It was a hard problem to start off with. And in fact, I think the hardest part of this problem was just setting it up. Once we get here, all we have to do is some calculus, some derivatives, and then some algebra just to solve the system. And then we should have the answer. That's the answer. Another thing that's, remember, don't get tripped up by is what are the choice variables and what are the parameters here, right? The only choice variables are C1 and C2. Everything else, well, lambda is a multiplier, Lagrange multiplier. Everything else is an exogenous variable or a parameter. Either way, you think of them as either one, but they treat them as fixed. So how do we do this? How should we get the answer? I'm going to. Should I keep going on this slide here now that I've written so much? Like here's LC1. That is the derivative of L with respect to C1. From this first term, I should get 1 over C1, I think. And from this, I get minus lambda. That equals, and that's, I think that, oh wait, I said C1. What am I doing? It should be minus, I'll say lambda 1 plus R. How about that? You agree? Taking the derivative of L with respect to C1. 1 over C1, that goes away. Here's a lambda, here's a negative 1 plus R C1. That's where the negative lambda 1 plus R comes from. No other C1s. How about LC2? From that, from this one, I get 1 over C2. You guys remember the derivative of natural log is just 1 over whatever the argument of the natural log is, right? That's another, let's be honest, that's another reason economists like to talk about logarithmic utility. It's because it makes the marginal utility so simple. You have a log utility function, then the marginal utilities are just 1 over the argument of the utility, 1 over consumption. So we economists are practical people as much as we can. We want to make our lives easier. Okay. Oh, I forgot the equals 0, didn't I? You want this trick to see, instead of writing equals 0, you can just make this equal, right? I'll do the arrow here. Agreed? Instead of saying this whole thing equals 0, it's like I've done one more step of algebraic manipulation just to say this equals this. And now I can see even further what the answer is going to be. In a problem like this, it's often very helpful to solve for lambda and then eliminate lambda. And the way to do that would be to take the LC1 first order condition, divide both sides by 1 plus R, and you'll get lambda equals here, you'll get lambda equals there. Then just set the left-hand sides of these two equations together, and you will get, oh, do I have space to write it here? Would you be okay if I wrote it here? I'm going to erase this whole stuff on the top so I have more stuff to write on the top. Move this to here. Okay, so I'm going to write what I get from this part up at the top. And that is from the first one, once I divide by 1 plus R, I get 1 over C1, 1 plus R, equals 1 over C2. Or in other words, If I cross multiply, I can get rid of the ones, right? Move the equal sign down. We found a very interesting and perhaps convenient result here, which I'll highlight in red. This result here says that my first period consumption times 1 plus R should be equal to my second period consumption. Oh, by the way, this is not an answer. This is not an answer to the problem, because you can't talk about one choice variable in terms of the other choice variable and think that that's a solution. It's not. It's just something I wanted to point out. Like, oh, that's kind of an interesting result. And look how this doesn't depend on M. It doesn't matter how much money you start with. If you started with all of your money in period 1 and none in period 2, or if you started with all your money in period 2 but none in period 1, either way, you're going to choose this relationship between C1 and C2. That's an interesting result of economics. It's called consumption smoothing, because if you expect a lot of money in the future, you'll spend more money now. Or if you expect to be very poor in the future, you'll save money now. Don't you agree? At least optimally, that's what you should do. Whether people actually do that is another story. Okay. By the way, though, you do see doctors, like pre-med students. Pre-med students are kind of poor because they have to spend money on their med school tuitions, but they still spend money because they expect to be doctors later. And that's just the idea of consumption smoothing, is that they spend money now, they borrow money now, expecting to have a high income later and be able to easily pay off whatever loans they were accruing during their med school years. I mean, I've never gone to med school. I don't know if that stereotype is actually true. Do med students just spend a lot of money even though they're relatively poor? I don't know, but I feel like that's kind of a stereotype. Okay, let's finish this problem. I'm going to finish it on the slides, not this, but we got here all by ourselves, right? C1 1 plus R equals C2. That's a nice result. We will continue. Clear. Let me get rid of these. Yeah, it didn't clear. You're all drawings. Okay. Now it cleared. This is another way I had of writing the budget constraint, using the point slope form of a line rather than using the slope intercept form of a line. You get the same thing here, if you can tell, pretty much the same thing as what I had. Here's a Lagrangian. Here's the way to write the Lagrangian. Here are the first order conditions of the Lagrangian. You get exactly the same thing that I got. And if you take the reciprocal of both sides, you get C1 times 1 plus R equals C2. So once we get there, which is what we got, plug that into our third first order condition to get this equation. This equation has a lot of variables in it. And you might say to yourself, what do I do? Well, at least we've eliminated C2 in this equation. That's what we wanted. If you pay attention to what's left in this equation, C1, R, M2, and M1, but that's it. There's no C2. That means we can solve for C1. Just move the C1s to this side and divide through, you get the answer here. This is actually the answer. And C2 is just 1 plus R times that. So we take each term and multiply by 1 plus R, you get that for C2. This is just algebra. I don't think I need to. I mean, hopefully you can see the steps of algebra just by looking at it. Do you guys have any questions about that? How you get to this answer from this problem? It started out as a problem about borrowing money or saving money across time, and what would be the optimal way to do that if you knew how much income you're going to get both periods, and you knew what the interest rate is going to be, and you have this particular utility function. How should you do it? Well, here's the answer. There's another way to interpret this. Have you guys heard of the present value of money? You've heard of this term, right? This right here, M1 plus M2 over 1 plus R, that is the present value of your income. Present value of income, which means in period one, you're thinking to yourself, what's the present value of all the money that I'm either have and I'm going to have? And that means you have to discount the money in the future by 1 plus R. This is exactly half of it. In period one, you consume half of the present value of your income, of your lifetime income. That's a kind of a neat result, and it's a result that says something about your income smoothing, consumption smoothing. Sorry, consumption smoothing. Can anybody see what's maybe wrong with this model that I didn't put in? Any ideas of? It's okay. If you go to grad school, you'll see this model, but just with more stuff added to it. More stuff. You keep adding things to it. One thing you add is a discount factor, and a discount factor says, my current self, like the me of right now, doesn't care as much about my future self as I care about my current self. It's just weird. It's a weird concept, but it actually makes a lot of sense. You think of all the ways in which you're tempted by something that you want to have right now, and you know that there'll be consequences later. You just don't care so much about the consequences because they're in the future. That's sort of, economists try to sort of capture this idea with what's called a discount factor, or your utility in the future is discounted. And if you apply to a discount factor to this problem, what you actually see is it's possible C1 and C2 are the same. They don't just differ by a 1 plus R. They could be exactly the same if your discount factor is equal to the interest rate, right? Of course, if your discount factor is more than the interest rate or less than the interest rate, it changes things. But that's a problem for if you go to grad school. If you go to grad school, learn that problem. But as an undergraduate, I don't think so. I don't think I have anything else to say about this problem. Do you guys have any questions about problems like this? Should we move on? What time it is? 1:04. I think we're ready to move on. And I recorded that, so you can always go back and watch me do that problem. If there was something, like Kai just came. She told me she was going to be late. Hello, welcome, Kai. I just finished doing a problem on borrowing money or saving money across time periods, and looked at the results of that. But it was basically the last problem we're going to do with a equality constraint. We're going to move on to inequality constraint. So if you're curious about it, I'll post a video, you can watch it, or just look at the slides. The next thing I want to go through is inequality constraints. Yes. Basically the last topic of the class. Last thing we're going to do this semester is constrained optimization with inequality constraints. What I have written in there on the. Everybody can see the slides. Jordan's, you're the only one with the slide. You good? All right. And the head nod is good. It's all I need. One person can see it. That means you probably all can see it. So let's talk first. Let's have a little chat here about what is it that we're doing and how is it different? And let's just talk about a problem, a generic problem where there's two choice variables, X and Y. You got your objective function F that you're trying to maximize, and you got your constraint function G. The only difference now, instead of G is equal to C, it's less than or equal to C. How is this different? Other than, okay, so yes, obviously it's different because there's a less than or equal to sign here, and there's an equal sign here. But do you think this actually changes what X and Y are? What do you guys think? I'm going to do my dog example and a bone and a chain. I always do it every year. If you've for some reason seen videos of me lecturing about this topic from the past, I don't know why you would have, but I have this example. Okay, so my answer is it might not be different at all if in the answer this g happens to be equal to c. If in the answer of the problem g of x and y, when you find x star and y star, you plug them in here, it's actually equal to c, then you could say it's exactly the same problem. Just because you could choose to let this left-hand side be less than c, if because you're trying to maximize this function, you decide I don't want to choose an x and y that would make this less than c. I want to make it something that's exactly equal to c. Then this problem is exactly the same as if it were an equality. The answer would be exactly the same as if this were equal or less than. However, it's possible that you want to choose an x and a y here that make this g function less than c, in which case, okay, so what should we say? So yeah, I'm making some assumptions here about f, like some monotonicity assumptions here, but pretty much you could say that the constraint isn't really doing anything. If I could choose an x and y less than c, x and y such that once I plug it into this g function, it's way less than c, then it's like I didn't need this constraint at all, because those are the x's and y's I would have chosen anyway. I'm realizing that you could probably think of an example where this is not true. I'm assuming now that there's like an optimal x and y, and there's one optimal x and y, and there's no issue where it's like a local max, but really there's a global max somewhere else. I'm sort of ignoring that. So if you ignore objective functions that have these local maxes which are not global, then if I'm choosing x and y and it's a global max of f, and this formula gives me a g less than c, what I'm arguing is that we could have ignored the constraint altogether. Does that make sense? I'm saying there's two possibilities here. One is that we can ignore this constraint, because if we just maximize f in an unconstrained way, we'll get the same answer. That's one possibility. The other possibility is that we can treat this as an equality constraint, because it will hold with equality, and we could use the exact same method that we've already learned about the constraints with equality. So I guess that's what I wanted to teach you. Even though, the truth is it's more complicated than that technically, because there are these possibilities with local max versus global max, or there's possibilities with just sort of non-smooth functions. But assuming these functions are smooth and differentiable, then I think what I just said is right. So here's how I want to talk about it. I want to use the word binding versus not binding. So if this constraint holds with equality at the maximum point, we say the constraint binds, B-I-N-D, bind. If the constraint does not hold with equality, it holds, G is still less than C, but it's not equal to C. Then we say the constraint is non-binding, obviously, not binding. The word bind is like, imagine you're a dog and there's a chain, and the chain is a 10-foot chain, and you're a dog. If you want to go 20 feet away, that's like, there's a there's a squirrel or something that you really want to get that squirrel. Maybe the squirrel is just lying there and easy to get. Well, if it's 20 feet away and you're the dog, you go all the way till the chain is tight at 10 feet. You can't go any further. That chain is binding the dog. Whereas if the squirrel is only 5 feet away and the chain is 10 feet, the chain is still holding the dog, right? The dog can't go more than 10 feet away. So the chain is still doing its job, which is to keep the dog at least 10 feet from the pole that the chain is attached to. But the chain is not binding. It's not binding the dog because the dog only wants to go 5 feet away, and it can easily do that with room to spare on the chain. So that's the difference between the words holding and binding and non-binding. So in the context of math, holding just means this inequality is true. It holds. Okay, so you always need the inequality to hold, right? The dog always has to be within 10 feet of the pole because that's how far the chain is. But it doesn't have to bind. And also it either binds or it doesn't. And it binds if the dog wants to go at least 10 feet away. If the dog wants to go 10 feet or more away, that chain will bind. If the dog doesn't even want to go more than 10 feet away, wants to stay inside 10 feet, then the constraint is non-binding. So let's try to use that word. I will use these words and hopefully you'll be familiar with them. I have some more slides about it. Okay, here's my answers. I tried to say this stuff in words, talking to you, but here it is written out in case you want to review. If this happens, we say the constraint is non-binding if G is less than C. Oh gosh, this should be a G. I'm sorry. Can I change that? Yeah. Changed it. If the maximum occurs when gxy equals C, we say the constraint is binding. But I like my example of the dog to really visualize what it means for a constraint to be binding and for a constraint to be non-binding. I think what I want to say in this class is I want to give you a method of solving these types of problems that's simple and doesn't go into the full complicated, what about this, what about this, what about this. If you go to grad school, you should learn that complicated method that's more comprehensive. You can solve any problem if you use that method. The method I'm going to give you doesn't necessarily work for every problem, but it works for natural, normal-looking economic problems, which hopefully that's what you care about, is being able to do this for sort of a real situation, economic type situation, where this almost like the objective function is something like a utility function, something where more is better and you want to maximize it. And then the constraint is something like a budget constraint, maybe something like an environmental constraint or some other type of constraint. But that's the type of problems I'm going to be giving you. I'm not going to give you anything really bizarre on an exam. Okay, any questions? You guys have any questions about this? Binding versus non-binding. Okay, here's a solution method. Okay, it's going to be the same as the one you already know, except in the case of non-binding constraints. If a constraint does happen to be non-binding, I should put an asterisk here, and the problem is not too weird, then it can be ignored and the problem can be solved without the constraint. And just for you guys, what I mean by weird is, it can't have too many different local maxima, because it could be that, oh wait, here's a local maximum, but there's even another local maximum somewhere else that's better. Oh well, if function is monotonic, it won't have these sorts of different local maxima. But I still agree with this point, which is that you can sort of ignore this constraint and still just look for what would be the maximum of the problem. So how can you tell if the constraint is binding without going through the whole problem? how can you do it? I'll give you a method. How do you find non-binding constraints? So now I'm going to talk to you about, okay, this is great. I'm just telling you that if a constraint is non-binding, I should put an asterisk there, and the objective function is normal, then you can ignore the non-binding constraint, and then the problem becomes easier. So how can you tell if a constraint is binding or non-binding? Here's my answer. You got to look for it. You got to try to solve it using the method of Lagrange multipliers. And you go through the steps of that solution. And if you ever get to a point where there's a contradiction or there's an error, it tells you something. It tells you, wait a second, the normal method isn't working, and it's because one of my constraints wasn't binding. Therefore, I should eliminate the non-binding constraint and start again. So that's my overall picture of what I'd like you to do. Let me be more specific now. If you think, like, here's a problem with the constraint may or may not be binding. Try to solve the problem just as before with here's 2 choice variables and 1 multiplier. You're going to have 3 equations, 1 for each first order condition, and 3 unknowns. The 3 unknowns are the 2 choice variables and the multiplier. If in the solution of the problem, lambda is less than or equal to 0, then the constraint was non-binding and should be ignored. Once again, I mean for the simple problems that I'm going to give you, should be ignored. That means you have 2 equations and 2 unknowns, which is something you can solve. Okay, so that's it happens when the multiplier is negative or possibly 0. But when the multiplier is negative, you know that this constraint was non-binding. And it will actually get you the wrong answer if you treat it. So let me say, if you're treating this with the same method that you did with the equality constraints, but the truth is one of your constraints was non-binding, and you ignore that fact, you would get the wrong answer. So you should not ignore that. You should eliminate the non-binding constraint from your set of first order conditions. And that instead will give you the correct answer. Okay, I'll give you some examples of this. So if in the problem there were multiple constraints, this is a more difficult case, which I did give you in number 3 of your homework. Your final homework set is due a week from today, and the 3rd problem in that homework set does give you, I was debating like, oh man, should I give them a problem with 2 constraints? And I said, yeah, I think I should, if you don't mind. I do ask you to do a problem with multiple constraints. So I'll make sure you know enough to be able to answer it. Okay, so once again, this final bullet point. If the problem started with multiple constraints, what should you do? You should create a Lagrange multiplier for each constraint. Instead of just 1 multiplier like we have in this example, you would be a 2nd multiplier for a 2nd constraint. You should solve the problem just as before with our method, but ignore any constraint whose multiplier is less than or equal to 0 in your answer. I wonder if I'm confusing anybody with the word ignore. Do you know what I mean by ignore? Ignore is a weird word because that's all about, like, mentally, what are you doing in your brain when you're thinking? And what I actually mean is something very specific and mathematical. So I'll try to be more precise what I mean by that. And in fact, I have here in this sub-bullet point. Look at the sub-bullet point. What I really mean by ignore in this case is to set the multiplier equal to 0. If you set, like, look at this L. If you set this multiplier equal to 0, what happens? You have the objective function f plus 0, plus zeros, a bunch of zeros. Isn't that exactly the same? Then you just have the Lagrangian is exactly equal to the objective function f. that's the same as ignoring it, isn't it? It's the same as ignoring it, because whatever is happening over here with the constraint, who cares? It's being multiplied by 0, and it doesn't affect the mathematics at all. So perhaps that's a more precise way for me to explain what I'd like you to do in these cases. Is really, when I say ignore, I mean just assign a value of 0 to lambda. Say lambda is exactly equal to 0. It will always be 0. From now on, lambda equals 0. That's the equivalent to ignoring lambda, because it won't appear in anything. Okay. Got it? You want to see an example? Right. Hearing me talk about how to do it is very different than actually seeing me do it and doing it together. That's what I would like us to do. I think that's the best way to learn. But here's a very easy example. I like to start with easy examples. I don't know about you guys. I like to start with really easy examples. It's so easy that there's only one choice variable. There's only one choice variable, and the constraint is just as easy as you could possibly get. Okay. The objective function here is 10x minus x squared. We want to maximize that function subject to, or such that, x is less than or equal to 6. This is actually a constrained optimization problem. It's very simple, but it is a constrained optimization problem. You have an objective function you're trying to maximize, and you have a constraint. You can use the method of Lagrange multipliers here. You might say, it's so easy, I don't need to use the Lagrange multipliers. Just do it anyway. What would the Lagrangian function look like? 10x minus x squared, that's the objective function, plus lambda, that's the multiplier. And now remember when I said it mattered whether you write the right minus the left side? It does. Assuming that the constraint is written in a way such that the left side is less than or equal to the right side, then you write it right side minus left. Here's one way to think about it. It should always be either positive or 0, what you have in here. So because x is less than or equal to 6, that means 6 minus x will always be positive or 0. In case you forget, that's a nice way to remember. Okay, so this is our Lagrangian for this case. As you might say, it's exactly the same Lagrangian you would have used in the previous method, right? The previous method where the constraints were equal signs rather than less than or equal to signs. This is exactly the same Lagrangian you would have created. So nothing's different so far. In fact, the next step is to take the derivatives of L with respect to the choice variables and the multiplier. Well, there's only one choice variable. Take the derivative of this, you get 10 minus 2x. Here's a minus lambda equals 0. That's the first order condition. What about the second first order condition? Just as before, it gives you this 6 minus x, but now it's equal to 0. Equal to 0. Yeah, because that's what you do with first order conditions. You set them equal to 0. If you solve these, you get from the second one. What happens here? The second one, we get 6 minus x equals 0. So you get x equals 6 as part of this solution to these first order conditions. What is lambda equal to if x equals 6? We'll take a look at this first order condition. You get 10 minus 2 times x. Well, x is 6, so that's 10 minus 12 minus lambda equals 0. 10 minus 12 is negative 2. Add lambda to both sides, you get lambda equals negative 2. You get this, lambda equals negative 2. This is where the method that I'm teaching you now kicks in. The method is if the condition is lambda cannot be negative. If you found lambda negative, that means the constraint was not binding and should be ignored, or at least, instead of ignored, I don't know what that means, but set lambda equal to 0. Okay, rather than lambda equals negative 2, this is not a solution. I want to annotate here to point this out. This here was a potential solution, which we checked it. Wait a second, is lambda okay? The answer is no, lambda was not okay. Lambda was negative. Lambda cannot be negative. Therefore, we just say, all right, we're going to set lambda equal to 0. Okay. This is like saying, oh, the dog didn't want to go. The chain and the dog wasn't actually binding on the dog. We were answering this problem as if the dog had reached the maximum amount of its chain and was trying to figure out where to go given that. But that was a wrong assumption. We shouldn't have assumed that, because the dog was still within the boundary of the places it could walk to, and it will just go straight there to that place it wants to go to and stop. So, and the way we mathematically do that is by setting lambda equals 0. And we can still use these same first order conditions. So this one we ignore because it comes from lambda. Once we have lambda equals 0, the first order condition also goes away, the ones for the lambda. From this one, if this lambda is equal to 0, it goes away. We just get 10 minus 2x equals 0. And that solves for x equals 5. And that's the correct answer. This is the correct answer to this problem, which you guys probably could have realized on your own without the method of Lagrange multipliers. I'm not saying you need the method of Lagrange multipliers to solve this problem. You could have done this probably in high school. If somebody said, okay, what's the maximum of this function? And oh, by the way, x has to be less than or equal to 6. You would say, okay, well, this is a parabola. It's maximized to x equals 5. And yeah, since 5 is less than 6, this doesn't matter. The answer is 5. Good. I wanted to show you an easy problem where this method works. What I really want you to, and if you have any questions, please ask. I want you to understand that it's because of this -2. Because of this -2 that we decided to get rid of FOC2 and to set lambda equals 0 here, so that part goes away too. Okay? And of course, the word is, it's non-binding. Maybe I should have put that somewhere on the. I don't think I put that on the screen. So I'm writing it in my big annotative way with my mouse. And I'll even things around it. If this gets to be the thumbnail of my YouTube video, I'm going to look like a crazy person, right? Why is he making such a big deal about this word non-binding? Because that's what this is demonstrating. I'm demonstrating to you, in this case, the x less than or equal to 6 constraint was non-binding, and that's why the answer was x star equals 5. Any questions? Do I look like a crazy person by having highlighted this word non-binding so much? A little bit, a little crazy. All professors are a little bit crazy. We wouldn't have been chosen as professors unless we had a little. Oops, I went to stop share. Let me go back. Slideshow from current slide. How much? 1:30. Oh, I have 15 more minutes. Okay, here's another very easy example. Here's another very easy example. The only difference here is I changed it from 6 to 4. X now has to be less than or equal to 4 instead of 6. Okay. Other than that, it's exactly the same. You see that? What's my method here? Well, just write the Lagrangian as you would normally. Find the first order conditions as you would normally. 10 minus 2x minus lambda equals 0 and 4 minus x equals 0. Solve these first order conditions simultaneously. Well, right here from the second one, we get 4 equals x. If we plug 4 back in here to x, we get 10 minus 2 times 4, which is 8. 10 minus 8, I'm sorry, yeah, no, that's right. 10 minus 8 is 2 minus lambda equals 0. That means lambda equals 2. So we have our solution is x equals 4, lambda equals 2. Notice here, I want to go a little crazy again. Lambda equals 2, which means binding. Okay, which is why we keep it in. Don't ignore the constraint in this problem. All I did was change it from a 6 to a 4, but that mattered. Changing it from a 6 to a 4 meant it's changed being from a non-binding constraint to a binding constraint. And therefore it has to be left in to our system of first order conditions, which is why we get this answer, x star equals 4. Now, once again, you guys could have told me this without doing the math. But here's the thing. this method works for harder problems where there's multiple choice variables and multiple constraints. And for that one, you couldn't just use your knowledge of high school math to solve it. Right here, I just want to make this point really clear with like maybe sharing what I have to do. New share. I want to show a whiteboard, right? Here's here, oops, this is a bad graph. This is the function. Oh gosh, I'm bad at this. Here's 0, here's 10. Here's the function f of x equals 10x minus x squared. The function 10x minus x squared is a parabola. It has this here, point here at 5. Can I do lines? I can do lines. All right, so the first problem was like, okay, x has to be less than or equal to 6. And I want to maximize this point. And the answer is, oh, obviously the answer is 5. And then the second problem was, all right, now x has to be less than or equal to 4. And the answer is, oh, well, now we can't choose 5. We have to choose x equals 4. And that's the difference between a binding constraint and a non-binding constraint. The red constraint is not binding because the optimal point is this blue point here. I don't know what that was. The blue dot is the true optimal point when we're talking about the red constraint, but the I don't know, I'm running out of colors here. The purple dot is the maximum point when we're talking about the green constraint. Green binding here, red non-binding. Got it? So this principle, if you understand this idea of binding and non-binding, it will help you do all of the problems, including the ones on the homework, including the ones where there's multiple choice variables and there's multiple constraints, because you get this idea where if, like in this case with the red line, you find that in the red line, the constraint is not binding, you set that lambda equal to 0. The lambda for that constraint, you set it equal to 0, and you ignore that first order condition and proceed. That's the method. Running out of time. So new share, back to the thing. How far can we get in 5 minutes? Not that far. Here's some technical stuff. There's something called the complementary slackness condition. I don't know if I really want you to worry too much about that. If you've understood everything that I've set up to this point, you don't need to know the sort of technical condition I'm trying to explain here why it's true what I said. I don't know how important this is. Like I said before, you write it so that it's always positive. The Lagrangian function should not be larger than the objective function. So if this is positive, that means lambda should be 0. But if lambda is positive, that means this should be 0. It guarantees that when you multiply two things, if you take two things and multiply them together, and at least one of the two things is 0, then the product is 0. That's what I'm trying to say here. And in math, we have a fancy term for this, and that's complementary slackness. And complementary means it goes together; they like work together. And slackness means there's some flexibility to what it could be, whether it's positive or 0. And the slackness works together between the multiplier lambda and this sort of constraint function c minus g of x and y. And the complementary slackness is at least one of them has to be 0. Okay, and the mathematical reason we can ignore non-binding constraints is that it doesn't change the value of the Lagrangian. In other words, if lambda equals 0, I said this already. I've already said, I think, everything on this slide. So if you understood it when I said it, I wouldn't move too much. But you might hear this in the future. Who knows? You may be in a class in the future and somebody talks about the complementary slackness condition from constrained optimization, and hopefully now you know what it means. That's 136. All right, Here's what I would consider to be an easy consumer problem with an inequality constraint. I actually think we do have time to do this because it's an easy problem. I gave you an easy one. Here we are with two choice variables, x and y. Notice they have to both be positive because we're thinking of like, how much x do you buy? How much y do you buy? You can't buy negative stuff in this case. And now we have a inequality constraint. X plus 2y has to be less than or equal to 10. What's our method here? Maybe you guys could tell me, like, what should the Lagrangian look like in this case? I'll give you a hint. It should look exactly like it did the times where this was in the equation, right? What is L equal to? Anyone want to guess? I think you know, you just don't want to see.
Is it xy plus lambda times -10 plus x plus 2y?
Did you say 10 plus x plus 2y?
-10.
-10 plus x plus 2y. Ooh, so close. Very, very good, but not quite. It matters now. Before it didn't matter, but now it matters. You want to do the right side minus the left. Okay? You said -10 plus x plus 2y. It actually should be 10 minus x minus 2y. One way to remember that is that it should be positive. So because 10 is bigger than this, this side should be, the right side should be subtracted by the left side. Looks like this. xy. So you said everything, but I would really recommend putting a negative sign in there. The reason it's important is because if you did it the way you were speaking of, this lambda would be flipped in sign. It would be less than 0. And I'm telling you that, oh, lambda, we need to find a lambda that's positive. So if you flip that, you're going to see lambda negative and think that it's not binding when it actually is. Okay, so the answer to this problem, from the first order condition, you get that y equals lambda. In the second first order condition, you get that x equals 2 lambda. Remember, like, eliminate lambda, you get x equals 2y. Plug x equals 2y back into the constraint, you get 2y plus 2y equals 10. The reason why we say it's equal to 10, I didn't write it here, did I? You guys see? Do you guys see what I didn't write here? Let me write it. I didn't write the FOC3, did I? FOC3, because I guess I thought it was obvious, was it's not x plus 2y is less than or equal to 10. X plus 2y equals 10, isn't it? You see why it's an equals here and not a less than or equal? It's because I'm getting it from this function here. I'm taking the derivative of L with respect to lambda, and it's giving me this. I'm setting that equal to 0. Maybe I should have written that way. 10 minus x minus 2y equals 0. I could have written it that way. But that is how we solve this. When we know x equals 2y, I'm going to plug 2y in here for x and get 4y equals 10. Divide both sides by 4, you get y equals 2.5. Then you know x is double that, so x has to be 5. So this, here, I want to take a step back and say, what if this problem didn't have a less than or equal to? It just had an equal sign here, right? That would be the types of problems you've already done. You wouldn't even need to worry about lambda. You would get to this point here and stop. X star equals 5, y star equals 2.5, you would stop. What I'm saying now is it could matter that this is a less than or equal to instead of an equal to. And that's why you have to check what lambda star is. You should go ahead and plug back in your x and y here to find out what lambda is. Well, it turns out y equals lambda, so lambda also equals 2.5. And because lambda is positive, this is a valid answer. Okay? Which means it binds. The constraint in this problem binds. Notice my last thing there, and it'll probably maybe be the last thing we do today. Whenever we have a monotonic utility function, in other words, more is better, like this, if our utility function is x times y, and the more x we get, the better it is. The more y we get, the better it is. And you have a normal looking budget constraint like this. This is like saying x plus 2y is how much money we spend on x and y, and 10 is how much money we have to spend, and we have to spend less than or equal to the amount of money we have. Okay. That's a normal looking budget constraint. Then the constraint will always bind. Why? This is my question to you now. Why? How do I know this? How do I know that the constraint will always bind in a problem like this? And we have an answer. Why? What do you guys think? No answers? I'm really trying to focus the viewer onto this word why. Well, I mean, answer like, what would happen if it didn't bind? Can you convince me that it's not possible that we could maximize our utility and have the budget constraint not bind? No answers. Maybe this question's harder than I realized. Think about it. If the constraint did not bind, that's like saying we're not spending all of our money. You have more money to spend and you're just choosing not to spend it. You might say, well, that might make sense. I don't always spend all the money I have. But in this problem, there's no future. There's no reason to save. And it's a monotonic utility function, which means more is better. Therefore, you're going to spend all your money and the constraint has to bind. If it didn't bind, then you could choose a different point and increase your utility. And because of that, that's how we know that the constraints will always bind. So in fact, this is kind of why I didn't give you a simple problem with just one constraint on your homework. Well, actually I did. The second one has one constraint. And I'm not telling you whether or not that one binds. You may have to figure that one out on your own. But the third problem in the homework set, I think it's homework set 6, has 2 constraints. And I'm not even telling you which one binds or which one doesn't bind. I think it's more of an interesting problem. And we'll have to talk about that on Thursday when you get looks like a mess. Clear my drawings. When you get this question of multiple constraints. All right. So here's what we'll talk about on Thursday. Problems like this that have 2 constraints on them, this constraint and this constraint. Like, oh, which one binds, which one, that whole thing. We'll do that next class. Okay, you guys have any questions about homework sets or the exam? I think Kai, you weren't here, but I told the class that I'll probably make the final exam available to you on Thursday, May 4th, which is what I thought the last class was going to be. VCU told me that the last class is now going to, oh wait, I said Thursday, May 4th. I meant Thursday, May 6th. And our last class will be Tuesday, May 4th.
When is it due?
I haven't decided. It's going to be a take home. It's going to be like you'll have multiple days to do it. I kind of want to see how long the exam is, and I don't want it to be rushed. So you'll have several days to do it. Probably the whole weekend to do it. If that's okay.
Okay.
Similar to the homeworks where it's not timed like the quizzes are. We just print it out and do it when.
Yep.
However long we want.
Yeah, this is going to be something where you write it on by hand and scan it and upload it, because it's a lot of math probably. I want to see your work, and I don't want you to have to type out all your work on Blackboard or something. So it's probably pencil and paper or pen and paper will be the best way to write your answers and upload them.